Hello my viewers from YouTube. I think I need to start this video by apologizing for just ghosting you all for the last few months, but I have been facing just a giant mountain of academic pressure, and that is really not optimal for a YouTuber, let's just say that. I remember in one of my videos I saw like a demo, and the demo is basically guy apologizing for not putting up a better demo because he's reviewing for his exams. That's exactly what happened to me. I'm still kind of brushing up my YouTube skills and like retro computing skills because, to be honest, I'm a bit rusty. So don't expect anything too crazy from this video. Don't expect anything too sophisticated. And unfortunately, this won't be a hack update. But if you stick around, I will talk about some thoughts I have with the project going forward at the end of this video. So in this video, I'll be talking about this computer and repair it. It's a Laser 310 or 310 or 310. I don't know how you say that name, but I think it's sold also in Australia as like the VZ300 or 310, or maybe just 300. I think there's a VZ200, which is sold also as the Laser 200, and that has basically the same hardware inside, but a worse keyboard. It's the same situation as the Auric computers in the UK, right? But when we open this computer, we will find a very interesting architecture inside. And I would say up front, this computer is basically working, but it had several keys just flat out dead. I cannot get them to work no matter what I do. They're like the 1 key, the 2 key, the Q key, the A key. I think these are one group, and the 9OL and the full stop key. They are not working. But otherwise, this is a machine that's basically in pristine conditions. It even has its covers for its cartridge connector zone, which is really rare for these machines because people would connect peripherals to it and just throw away the backplane. And these are screwed on, so once you put something into the bag, there's no place to store it, so people tend to just get rid of them. But yeah. Oh wow. Let's get the camera closer. I literally just discovered that on the back there's this switch labeled C and BW. I guess it's just for color or black and white. I never knew there was this switch here before, but hey, we all learned something new. But let's loosen the screws and open this thing up. Okay, now we are in. Well, I would say the condition inside is good, but obviously either some of these ribbon cables are broken or some traces on the keyboard are broken. I tend to believe it's the latter because I've heard reports saying that is the case. Unfortunately, there's this metal shielding. I am a professionally trained electronic engineer, so I kind of don't like the idea of removing the shielding from the machine. I kind of like shielding. So I will try and disassemble the keyboard PCB. I really need a smaller screwdriver for this. Now the really annoying thing about this shielding is that you can see it's soldered on. So that piece of solder coupled with the shielding has quite some heat mass. And it will kind of make a mess if I want to remove the shielding. Unless there's something wrong with the motherboard, which in my experience just doesn't happen that often. I'm not going to remove it. But this shielding also obstructs something very interesting about this computer, which is its graphics chip. The graphics chip is the MC6847, the same graphics chip used on the Tandy color computer. The MC6847 is kind of the weirdest, whether you call it CRT controller, like 8-bit graphics chip or whatever, out there, because it does not sit on the data bus. Well, it does. It sits on the data bus to read the character data, but it does not present any registers to the CPU to let you configure it. So if you program for the Commodore 64, you program for the Nintendo Entertainment System, if you program for basically anything that has a graphics chip in it, even like the IBM PC has a CRT-C chip, there are registers that you can write to control the behavior of the graphics chip. Now, what the 6847 has are input pins. No. Input pins that you can use to configure things like graphics modes, character attributes, and other stuff. And this makes it pretty hard to work with because you need to kind of pair it with an external kind of I/O controller to present the setting to the CPU. And the common way to do it is to use the MC6883. I think it's called the SAM chip. And the SAM chip is used in the Tandy color computer. The whole thing is basically used as a chipset. One SAM, one 6809 CPU, and one 6847, I think it's called a VDG, Video Display Generator. But on this machine, the 6847 is used with the Z80. And to be honest, I still don't know who came up with the idea, because the 6883 is obviously closely tied to the 6809 architecture, so you cannot use it on here. Laser or VTech, which is the company that manufactured this computer, must have some pretty clever methods to share the data bus between the CPU and the VDG. I may understand why they chose to do it, because the VDG has its internal font, which saves the cost for a font ROM. But the problem about that is there are other chips that eliminates the need of a separate font ROM. For example, the Texas Instrument TMS 99810, very commonly used with the Z80. And that chip has fonts in RAM. Of course, you still need to store like the font in your boot ROM, but your boot ROM is usually like 16K or sometimes 32K if you want to include a BASIC in it. And there's usually enough space to store like an ASCII font in there. So I cannot find a very good reason for using the chip. I guess it was just really cheap back then. And the Laser 200/300/310 series is like a series of really cheap computers. Ooh. Who would have thought this is a bad idea? Let's try this. I'm making it worse. Try to rotate the board. Doesn't even seem to rotate with the board. Oh, wait. I may have destroyed it. I may very probably have destroyed this one screw. What are these? I think these are kind of jumpers? Look, if you think this thing is like upside down, then we have I think this strip being bad, and these part 1, 2, 3, 4 being bad. No, I'm looking at it completely backwards. Okay, it's this strip, or maybe this strip. Yep, it is this strip. It makes sense now. It's this strip, and 1, 2 QA, which are this one, this one, this one, this one. Okay. All right, here's what I'm thinking. Our primary suspect are these jumpers. I just cannot trust these jumpers. So let's first test things like this one to this one. Going all the way to, oh my, look, this goes all the way to this. Not this, but it goes to, but this is the 2 key. Hello, I think I have something. This one is broken. Unlike things like this one, or this one. This one is just, it's just completely broken. All right. Does this solve all of our problems? I doubt it. What connects this one, this one, this one, this one together? It is this, right? No. But it also connects this together. And goes all the way. It's the space bar. I don't think the space bar is problematic. but I can be wrong. But if there's some connection problem with this, it's unlikely because it's just all the way trace. It's a trace all the way there. Yeah, it's a trace. I have to say, this one might be our suspect. Yep. This part is connected to this half, but not that half. I think the right thing to do is to kind of reinforce all of these. Because I think it's fair to say that all of them will break one day. So let's bust out the soldering iron. Oh my! Oh my, I actually cut the trace by heating it up. That's just how fragile this is. It's some kind of paint. I think it's just conductive paint. All right. Solid. 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 Oh, not this one. Solid. 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 Okay, these are not connected. Yep. Okay, all solid, all complete. I would say the conducting paint smells horrible. I don't know whether I ingested some just toxic fume for doing this, but all of those points are tested and working. Alright, it's now fully functional. Let's put the rest of the screws back in. Oh my god. Now this thing is fully fully in there. It will not come out. Leave your objections in the comment section below. If you have any good idea to deal with such a screw, please tell me, because I've faced this situation more than once in my experience fixing these retro computers. Hey, this thing loose inside. Hey, we have a machine. All right, moment of truth. The color is a bit wrong because the table is kind of magnetized, but if we ignore that, let's try to hit some keys. Okay, control key works. Shift key works. Right shift works. Space key works. Yay! This thing is now fully functional. And the repair is a success. Alright, so what about the hack? Now, before I get into that, I think I need to restate the goal of the project, or should I say a non-goal of the project. It is deliberately a non-goal of the project to build a Z80 with protected mode support. The goal has always been to use the Z80 and kind of exploit its signals and use clever ways to fake kind of a protected mode. But in my original Z80 video, I claimed that this thing would make it, well, not this thing, but like my hack computer would make it a virtual memory machine. Now, from the beginning, the memory is virtual in the sense of the address that the program sees, or memory pointers that program sees, is not the physical address of the variable in the physical memory. That's just because of paging. But another important definition of virtual memory is that memory can be brought in on demand. And that creates a problem because a ZAD instruction is atomic. That's a good thing because otherwise I would be dealing with 1,000 edge cases every time I want to do anything with interrupt. But that also means an interrupt is not accepted until the instruction has finished. That means if an instruction accesses a memory that's not there and it triggers a bus error interrupt, the operating system will go in, read, for example, hard disk, and populate that part of memory and restart that instruction. However, that instruction will actually be run twice and once, and one of those times is with an invalid memory value. Now, for most instructions, for example, a load from memory, if something is loaded into the A register, then if the instruction is restarted with the correct value, then everything is fine. Then the wrong value will be overridden by the correct value. However, if the instruction is, let's say, end, it will end the register, the accumulator, with whatever value it read from an invalid memory address, which can be anything. I can force it to 0, or I can force it to binary all ones. I can force it to whatever. And instruction will calculate the result and put it back into the accumulator. That is really bad because if I end with all zeros, then the result is 0. And if I brought in the correct value, and that is not 0, and the result can be something else. But if I restart the instruction, it will end 0, because that's now in the accumulator, with the correct value. But it doesn't matter. The wrong value is already there. All right, you might say, then maybe let's default to FF. The problem with FF is that you will soon realize that if you do an OR with that instruction, well, then you run into the same thing. Exactly the same thing. And what if the CPU tries to fetch an instruction from an invalid memory address? Now, I'm lucky because I can default the read to a value of 00, which is no op on the Z80. However, some Z80 instructions are multi-byte, and that means it might not be the opcode that the Z80 is fetching from an invalid memory address. It might be an operand, which can be any kind of stuff. Most of the time, it's a memory address. But some instructions are prefixed with DDCB, or I think EDCB. And those instructions have opcodes after the operand. It's getting a bit messy, but if I feed a 00 to it, it will destroy some processor state that I cannot restore in the operating system. So, what to do about it? My solution is to use some kind of programmable logic like a Gao chip to detect those specific instructions and feed specific values to the CPU that will kind of nullify those instructions. It's kind of building a board pin that's found on the 65816. However, that kind of violates the design principle of not building an entirely new CPU, because I'm essentially building an instruction decoder that's outside of the CPU. So it's violating the goal of not building another CPU. And that's only one problem. And the second problem is that with the current design, the HEC is completely unable to run CPM. And that's because of a very stupid reason. The CPM puts its file system interface, called a file control block, in an address that overlaps with the NMY vector on the Z80. And that is super annoying because the entire concept of protected mode relies on the fact that I can use the non-maskable interrupt that cannot be touched by any user program. And all Z80 program needs to use that interrupt. So my solution is something called the out of context interrupt, which means when the system receives a non-maskable interrupt, it actually switches to a different process before it responds. And that opens another can of worms, because when the Z80 receives a non-maskable interrupt, just like receiving a maskable interrupt, it will first try to store the PC value by pushing it into the stack. And I have no control where the stack pointer is for the user program. So if a user program receives an interrupt, non-maskable interrupt, and the whole address space just switch to that of the operating system, then the program counter will be written to some random address in the operating system address space that is full of very critical system variables. And that has the potential to just instantly break the system. That is not good. And the solution of that, I spent 1.5 years bashing my head against these problems. I have solutions. Is to have extra registers that's outside the CPU to catch the program counter values when the CPU just received a non-maskable interrupt. However, that's kind of, again, building parts of a CPU outside of a CPU. So at this point, I am just teared. I'm really clueless about what to do next. Do I keep a minimalist vision about this system and say, okay, these are its limitations? It cannot run CPM. It cannot handle all the edge cases. It cannot have true virtual memory. Or do I do a maximalist route and say, I will do all of these because I have laid out circuit to do all of these. It's a bit messy. It's not, by some margin, it's not the most complex supporting circuit for Z80 I've ever seen. If you get a picture of the NEC PC8801 motherboard, that thing is crazy. It is 7-4 logic city. And I'm not even planning to do that. But I do believe if I go the maximalist route, I would have lost my original vision of a very engineeringly elegant and minimalist solution that vastly expands the horizon of what is possible on a Z80. But I guess that's all. I've kind of rambled on a bit more than I originally expected, but I'm not going to edit it out because this is a low effort video. I'm Andy, and I guess I'll see you in the next video.